Bonjour tout le monde. Ça me fait très plaisir aujourd'hui de souhaiter la bienvenue à Ken Gayley, qui est professeur à l'Université d'Ohio. Iowa, sorry. J'ai bien de la misère, sorry. So Ken started out as an undergrad in Princeton, I'll change in Princeton, and then he did a PhD in California, University of California, San Diego, in solar astronomy. Very diversified pathway, you'll see. Then he went to Boulder to do work on cold stars, where he met Paul, I think, at that time. And finally, we got into massive stars when he went to do a postdoc at the University of Delaware with Stanowaki. That was when I met him. In Montreal, we were working on this new thing called clumping in winds, WR winds in particular. So we were mainly an observational group, and Stan's group was mainly a theoretical group. And we had these meetings in the Laurentians, and it was great stuff. We exchanged a very small group, and this is where I met Ken. So Ken is one of these he's very diversified, but theory-based, but still appreciates the observations. We're now involved in some polarization, proposing some polarization missions, and is going to be leading this. And also, this is why he's going to be talking about polarization. The title I had was Polarization,
Second spectrum.
Second spectrum, yeah.
Right.
So take it away.
Yeah, I saved that. You'll see why I saved the title for later. But
okay.
Yeah, so I'm a stellar physicist who does theory, and but of course observations are the truth. So we need to constrain that with our theory. And so we do astronomy, right? So what does astronomy mean? Well, the word astronomy literally means the laws of stars, even though today it's come to mean quite a lot more than that. But it started with stars, and how do we learn about stars? We look at light. That's astronomy. We look at light, and if we're looking at the brightness of the light as a function of direction or angle, we call it an image. That's what an image is. If we look at it as a function of wavelength or frequency, we call it a spectrum. So those are our tools, images and spectra. And what we have to do with it is we have to figure out what stars are. Well, there's only one star that we've ever seen up close and personal, and that's our own star, the sun. And even that one, when we got to look at it through Galileo's telescope, it came as a bit of a shock. So what about all these other stars that are just points of light in the night sky? What kind of surprises do they hold in store, and how do we see them when they're so far away, so small? Well, one way is the HR diagram, our best friend of looking at line spectra, figuring out the luminosity and the temperature of stars. And even that gives us some surprises when we look closer. With Gaia, we get the distance of these stars much better now. And so we can figure out their luminosity more precisely. So there's less scatter in the HR diagram now. And a big surprise from Gaia is when you look at, Gaia has some weird way of doing an HR diagram, but basically the zero here is about the middle of the B star regime. So when you get to the B stars, you see that the main sequence begins to split into almost a tuning fork. And so these are the early Bs up here. And so it's very clear that there's two flavors of massive stars that are different in the HR diagram. And you also see a lot of scatter in the turnoff. So this is an open cluster, it's a single cluster, that's why there's not that many points. And it's all the same age, so it should have a main sequence turnoff. But the main sequence turnoff is rather spread out. It's not just like the skin peeling off a banana, the way we normally teach it, because there's obviously something else going on that's complicated. And that thing that's going on is probably the same thing that's splitting that main sequence into two pieces, because you can look at the line profiles from these stars. And they ought to look like this, very narrow lines, if the stars were not rotating. But if you fold in some rotational broadening, and not even a whole lot, that's only 40 kilometers a second, you see broader lines. But the lines from the stars that we saw in that split part of the main sequence are more like 200 kilometers a second. So they're extremely broad. And that's also probably the explanation for the turnoff that's all scattered, is there's a range of rotation. But going back to that split main sequence, the thing about rapid rotation is you can see it from all different inclination angles. So if you see it from the pole, it doesn't make much broadening in the lines because the Doppler shift is only line of sight. You see it from the equator, you get a huge broadening. So it's hard to tell the rotation from the line profiles. But by an interesting accident, the way it works in the HR diagram is if you see a star from the top, it will be gravity brightened from the top, and we'll talk about that in a moment, but the light gets up more easily through the pole. So it will look brighter from the top. So its luminosity will go up if you see it from the top. If you see it from the side, you'll see the darker, cooler equator, which will make it redder. So if you see it from the side, it will move to the right in the HR diagram. But whichever angle you see it from, it takes the non-rotating main sequence and just shifts it to the rotating main sequence. So because of that accident, you see this gap in between when you have two populations, one which is rotating and one which is not. And you wouldn't see that in the rotational broadening because of the inclination confuses it. So it seems that there must be something happening to these massive stars where if it happens, they rotate fast. If it doesn't happen, they rotate slow. So that is an important thing that we want to understand about these stars. Okay, so at the rotating stars, but we all know that stars are spheres, right? The ancient Greeks knew that stars were spheres, so we could try to look at them with interferometry. If they're nearby, we can see, we're starting to be able to see stars now using interferometry. But what are we going to see, right? We're going to see some sphere like everybody expected. No, that's not what we're going to see, because these are very, very fast rotators. They look like this, and this, and this. This is what those fast rotating stars look like. They're very oblate. The equatorial radius is almost 1.5 times the polar radius, which is the signature of a critically rotating star. And they show what I mentioned before, this thing called gravity darkening, which is a darkening of the equator and a brightening of the pole. That happens because if you make your star very oblate due to the centrifugal forces of rotation, it will allow the light to escape more easily through the polar regions than through the equatorial regions. So this is not at all what you expect a star to look like if you just think of the sun. And that's one of the ways that we know that these massive stars are a bit different. But these are only the closest ones. These are mostly A stars or few B stars. There's just not that many stars that are close enough for us to use interferometry. Nevertheless, we can do that. And one of the type of stars we use interferometry to look at is a BE star, which is a star that has a disk around it. It's rotating so fast that it's believed that it's spinning out the disk. The disk is emerging through the equator, which is critically rotating. And this is phi per, which is a binary. So you have a B star with a companion. And so that's what interferometry looks like. You get the sense of this. In the lower picture here, we're sweeping through the H alpha wavelengths. So we're crossing the line in H alpha, so we're seeing different Doppler shifts. So that's why what we're doing is tracing out different parts of the orbiting disk. It has different Doppler shifts depending on where you are in that orbiting disk. And you see the disk up here in this one. There's the BE star and there's its disk. You're literally seeing the disk. It's not a great picture, pretty blurry. This is what you get with interferometry. It's really just barely able to see it. But you can tell certain important things, like you can tell that the orbit of the companion is aligned with the disk. So it certainly seems like the presence of that disk is closely related to the presence of that companion. Furthermore, the companion is a stripped star. It wouldn't evolve that way. It's basically just a core with no envelope. So these two facts strongly suggest that this phi per is telling us how it got to be a rapid rotator. It stripped the mass from the envelope of its companion in some sort of binary interaction. So that may be a critical way that stars acquire rapid rotation. But this is one system. It's phi per. It's close enough that we can actually see this with interferometry. How much more do you want to know? Well, another thing you can do is you can go into the time domain and do photometry. Because if the star has a spot on it, which massive stars weren't supposed to have, but there's various ways now that they seem to be pulling it off, and that spot is rotating, then in the time domain, your photometry will show variations. You could also have variations coming from a disk, because these disks have structures in them that might be sort of equivalent to spiral arms going around the disk, which would also cause behavior in the time domain. What's tricky about the time domain is this is Gamma Cas, which is a BE star. So it's a B star with a disk. And you see a bunch of different periods in the bright data. And it's apparently not that easy to tell which one is the rotation period of the star. But at least you're getting evidence there in the time domain that something's going around. And one nice thing about being in the time domain is you don't have to worry about the inclination. You see a signal that's periodic, and it's the rotation period you're seeing, then that's the rotation period. You don't have to worry about what the inclination is. So the time domain has something to tell us about these stars. So what are the kind of questions that we want to know? We want to know, how did stars get to be rapid rotators? So a clue from Phi curve, binary interactions probably play an important role. How about how long do they last? Once they become a rapid rotator, is that a lifetime sentence of rapid rotation, or do things happen where it will lose that rotation? What does this do to the internal physics? When we're learning about stellar evolution, we have these nice round stars. What about a rapidly rotating star? Does that evolve any differently? How about the type of supernova? When the core explodes, is the core rotating with the rest of the star? Or does the core remember a history that's different from what the envelope is doing? And finally, what does this have to do with the rest of the galaxy? So this is why we study stars. It's because the stars play a role in the whole evolution of the galaxy, especially massive stars because of their supernovas, chemical enrichment, and so forth. How does that affect things? So now that we understand that a lot of these stars are rapid rotators and it might change their internal physics significantly, we now have these questions. So how do we get our answers to these questions? Well, as we said at the start, theory can only do so much. The theorists can postulate anything they want. The question is what's really happening. So we need observational constraints. Things like how close to critical. Critical rotation is when the centrifugal force at the equator balances gravity. So the gas at the equator of the star is literally in orbit around the star at the equator. But does it have to be equal to that in order to spin out a disk? Or can disks start to appear when the rotation isn't quite that fast? That might change the effect on the internal physics. How about the gravity darkening that I mentioned before, where it's brighter at the poles than at the equator? We have two theories for that. One is the so-called von Zeipel theory, which is a very simple way to handle it, and it predicts a certain contrast in brightness between the pole and the equator. There's a more advanced theory by Lara Espinosa, that's a very recent theory, which suggests less contrast between the pole and the equator. And this turns out to be quite important because when the effective gravity at the equator is very weak, and these are radiatively driven winds, then if you have a brighter flux coming out the equator, competing against a really weak effective gravity, then you could get a very strong equatorial wind. So whether you use the simple von Zeipel approach or the more complex Lara Espinosa approach, it's very different predictions about what kind of winds these stars are going to have. And also, it's a hint of what's happening in the interior. You only see the surface of stars, unless you can do a little astroseismology to try to penetrate in there. But what's happening in the interior is what really counts. So how do we connect the surface to the interior, and understanding the gravity darkening might be crucial for that. And as I mentioned before, we don't even know if the stars are rotating like solid bodies, or if the core remembers a different history from the envelope. And a final key point that's worth some stress is chemical mixing. Because if you've learned in your stellar evolution class, the chemical gradient inside a star, the way the helium piles up in the core, has a very dramatic effect on the way the star evolves. It causes the star to reverse directions, and it's retracing its steps on the main sequence, post-main sequence. And that's entirely because of the helium content of the core. So if you have mixing due to rapid rotation, you should expect a completely different evolutionary path. And so we need to understand how much mixing is happening and why in some of the stars. So these are the fundamental questions that we want to get at by looking at these rapidly rotating objects. Okay, so we've got a lot of tools. We've got spectra to see the rotation broadening. We have interferometry where we can essentially image the star. And we have this time domain photometry where we can do astroseismology and look at spots going around. That's a ton of information. So what's the problem here? Why are we not finished with that? And the answer is ambiguity. Because even if we have all these different observational constraints, we have more questions than answers. And so the game that you typically play with this is you say, okay, I've got 3 or 4, whatever it is, observational constraints. Therefore, I will generate 3 or 4 theoretical questions, meaning 3 or 4 parameters in a model that I can use those constraints to fit. And that's a good way to approach the issue. But you can see immediately the 2 problems that you face when you do that. What if you have more than 3 or 4 observational theoretical questions, theoretical things that you don't know about that star? What are you going to do? You have to pick and choose. You have to say, well, I'm pretty sure about these 2 or 3 things, but I'm not sure about these other 3 or 4 things. So I'm going to let those other things be my parameters, the knobs that I can turn in my model. And the other ones I'll just take as a given. And this has been done throughout the history of astronomy over and over again. And quite a few times we've chosen the wrong things to take as fixed, like the fact that the stars can't be ridiculously far away, so the opposite stellar parallax means the Earth isn't moving. Classic example of taking the wrong thing as known. So you have that problem, it's what to treat as known. But even if you have the right choices about what you know, there can still be ambiguity. If you're fitting 3 parameters in a model to 3 observational constraints, there can still be a range because of uncertainties in the data. There's still a range of fits, and you still have ambiguity. So the bottom line is, I want to convince you that we need more observational constraints than what we have right now. And to show you that, here's some examples of what's been learned from interferometry. So we have 2 A stars, so this gets the idea. The B stars are the ones that we're more focused on, but A stars are more numerous and a little closer as a result. These are only 49 light years away. So we can start to do some good interferometry on these. And these are very rapid rotators, as you see from their pictures. They're quite oblate around the equator. And they're gravity darkened, especially alpha Cep. It's obvious that alpha Cep is got something that looks like a equatorial darkening due to its oblateness. And so the way we model that typically is with this beta parameter, which is the x-axis parameter here. The beta parameter is a power that you take the contrast in brightness between the pole and the equator, and you raise it to the power beta, because it's a nonlinear connection, to the temperature. I'm sorry, you take the, I said the brightness contrast, I meant the effective gravity contrast. The effective gravity is easy to calculate because you know Newton's gravity and you know centrifugal forces. So you get an effective gravity which combines real gravity with centrifugal forces. And you look at the contrast in that, the effective gravity between the pole and the equator. And then you expect some nonlinear connection between that and the temperature, which relates to the brightness contrast. And so that's what the beta is. If beta is big, it means there's a lot of contrast in temperature that comes from a given contrast and effective gravity. And in fact, 0.25, which is over here on the right side, is the von Zeipel. The sort of simplest way to do this is all the way on the right. The Lara Espinosa is around 0.18 or 0.19, so it's closer to the middle, slightly to the right. So think of the theoretical uncertainties are pretty much spanning the whole right side of these figures. But you could go all the way to none, which would be the left side. The left side of the figure would be, yeah, I don't think there's any gravity darkening. I think the whole gravity darkening thing is a big red herring for some reason. And so then you could be all the way over there. So in principle, you could have any gravity darkening, but it looks like, okay, at least for alpha Cep, we can rule out the absence of gravity darkening. There is some there. But the range goes completely from 0.25 to 0.19, which is the range of these 2 different models of how gravity darkening works. You just can't use interferometry to distinguish between those 2 models. And the green bordered area here is when you throw in the line broadening from the spectroscopy. So you got your spectroscopy, you've got your interferometry, and all you know is the star's information is somewhere between 40 degrees and 65 degrees, and somewhere between the Lara Espinosa and the von Zeipel gravity darkening. So you've learned a lot about the star, but you haven't learned the answers to these unknown questions. So that's the problem with ambiguity. So what's the solution? Well, for that, I'm going to have to put on my dark Brandon sunglasses. And the answer is the second spectrum, which is polarization. Okay? So the way polarization works is the light coming up through the star is scattering off its atmosphere. And depending on that angle of last scattering, if it comes from the top and bends toward you, you know that a wave moving up this way will cause the electron to oscillate horizontally, and that will produce light that's polarized horizontally. Whereas if its last scattering is out on this side and comes toward you, then the light wave is causing the electron to oscillate vertically, and the light signal that you see will be vertically polarized. You see, the problem is there's something about light that we haven't been including. We talked about the brightness as a function of wavelength and angle, the spectra and the image. But we've forgotten that light has another property, which is polarization. So that's the second spectrum. And so the way it works is if you look at the spectroscopy of this, if you take a given wavelength and sweep it through the line, and you're sweeping through the Doppler shift of the rapidly rotating star, and you get those broadened absorption lines that we talked about. But if you look at Q, which I'll talk about in a moment, is a measure of the polarization, then you see a totally different thing. When you're over on the right side of the star, you see the vertical polarization, which shows up as a positive signal here. As you move towards the center of the star, you see the horizontal polarization, which is Q, which I'll explain as soon as I'm negative. And then you come over to the right left side again, you see the positive. So in the light, there's both this information, the line absorption profile, and this information in the polarization. And we've just been sort of throwing out that second profile, second stellar spectrum. So how does this work? Well, these are models of the effective gravity of a very rapidly rotating star. So this is 96% of critical, meaning that the frequency of rotation is 96% of what we need for the equator to be in orbit around the star. And that causes a huge obliqueness in the star. And this grayscale here is the effective gravity, which sums the actual gravity to the centripetal force. And so you see the effective gravity gets very weak near the equator. The polarization vectors come from that scattering process that I mentioned. And so now if we superimpose those on the gravity darkening that comes from this effective gravity, you see that the horizontal polarization favors the bright regions, where there's a lot of light escaping, and the vertical polarization favors the dark regions. So by separating the horizontal from the vertical polarization, you can tell how much contrast there is between what's happening in the pole versus what's happening in the equator. So the game that you're playing here is you're trying to find a new way to get spatial resolution. The fact that over the surface of the star, the polarization changes direction means that when you're looking at polarization, so how do you do that? You use your filter. You say, oh, my sunglasses this way will filter out everything that's horizontal, so all I'm going to see is the vertical. So hold my sunglasses like this and see the light that's coming from here. Now I flip the sunglasses. It's now going to take out everything vertical. Now I'm going to see the light that's coming from up here. So I just go from this to this, and I'm changing my perspective on the star from this to this. So I'm achieving spatial resolution by turning the alignment of my polarizer. And that works at any distance. Unlike interferometry, which only works for nearby things, they need to be fairly big or else you'd never be able to do it. This could be anywhere, it could be in another galaxy. All you're doing is changing the orientation of your polarizer. Unfortunately, it takes a lot of photons to do this. So it's very hard to do this for stars in other galaxies. So you end up still looking largely at nearby stars, but the constraints aren't quite as severe as they are if you're trying to do it. Okay, so this shows you the same idea again, except at a different inclination. Before I showed you more or less from the side, but if the star has an inclination, then the brightened pole will be up there, and the darkened stuff will be down here. But even so, you can see that this star is going to produce a net polarization that's horizontal. because a lot of the light from the star is coming from light that shows horizontal polarization. And so, okay, so that sounds kind of interesting. So why haven't we heard more about polarization? Polarization is a relatively small subset of how astronomy is done. Why is that? And that's because it has a fatal flaw. And the fatal flaw is its vector quality, which means it suffers from a great deal of cancellation. So if you just look at this picture of the star and you can't resolve it, let's say you're doing a continuum measurement where you just get all the light that you're seeing. Then you're going to get the light from here, which is vertically polarized, and the light from there, which is horizontally polarized. When you add them together, if there was no contrast in the brightness, if this was just a white cue ball, then they would completely cancel. And even in this case, there is not complete cancellation, but there's a lot of cancellation. Even the light that's coming from these regions up here near the limb are still only a few percent polarized. So even the local light coming from the star suffers a lot of polarization cancellation. But that gets even worse when you sum over the whole star. Now you get tons of polarization cancellation. So that's its problem. The signal is weak. But that's also its whole point. Because if you're trying to contrast a rapidly rotating star from a non-rotating star, that's the main difference. The main difference is that a non-rotating star would be a spherical cue ball. It would have nothing to distinguish any direction from any other direction, meaning that the polarization would be zero. So you have a very weak diagnostic, but if you see it at all, it means you have a break from spherical symmetry. So polarization is an indicator of a break from spherical symmetry. Spherical cows are unpolarized. And so although the signal is weak, it has, it really labels the fact that I'm looking at aspherical behavior. Okay, so let's make sure we understand a little bit better exactly how this works. So the idea is I mentioned this Q. What is Q? Q is you take your instrument and you take the light from the star and you block out everything that is horizontal. And what you end up seeing, you give a positive sign to. So what you're giving a positive sign to is everything that has vertical polarization. And then you rotate your polarizer to block out everything that's vertical. And so now you see the stuff that's horizontal, and you give that a minus sign. And so you're subtracting. You're doing a subtraction between the vertical and the horizontal polarization, and that's called the Q. And so that contrasting sign that you're imposing yourself, you've just decided to do that, but the contrasting sign that you're imposing interacts with the contrasting brightness that comes from the break in spherical symmetry to give you a net signal that would have been zero. Now, you don't necessarily have to do this with vertical and horizontal. You can also do it with 45 degrees. If you do it at 45 degrees, you block off everything that's going this way, block off everything going this way, letting through the stuff, block off everything that's going this way, letting the stuff come through that's this way, you give it a plus sign, and then you rotate 90 degrees, and you're blocking off everything that's going this way, letting through the stuff that's going that way, and you give that a minus sign. And so you make a subtraction between this, and that you call the U. You're just doing that yourself, but it's useful to do that because what you've done is you've looked for any contrast between what's happening on the right side versus what's happening on the left side. Now you can see in this case, since you're just doing a continuum, you're getting all of the light. There's not going to be any contrast there. There's a symmetry, the left-right symmetry. So your U is going to be zero. So the Q signal will be big and the U signal will be zero when you have a rapidly rotating star and you have found the right direction for the axis. Of course, you don't know that. When you look at the star, you just pick these at random, but you can rotate it after the fact. You can say, oh, I got a non-zero result both ways, but if I were to rotate it this way, I would get zero for the U and something positive for the Q. So then you know, okay, that's the axis of rotation of the star. So we typically just define, we assume we've done that, we'll just define Q to be the one that aligns with the rotation axis. So you get a net signal in Q and not in U when you have a rotating star. So that's, in a sense, the beauty of polarization. It's a signal that is tuned to be zero almost all the time, unless it's exactly what you want to know. That's where they come out to 0. Problem is it will be a small signal. Okay. All right, so getting back to the ambiguity problem, our whole goal in all this is to be able to resolve ambiguity. We use polarization to resolve ambiguity. So I haven't done this calculation yet. I need to do this calculation to make this a little bit more precise. But what I want to stress for you, let's see if we could look back at these pictures. You can tell that, let's say you're not sure the contrast, how much brighter is the pole versus the equator. You're also not sure what the inclination is. How are you going to get a big Q signal? You're going to get a big Q signal if there's a lot of contrast. So in other words, a large beta, the beta more like the von Zeipel 0.25. That's going to give you more Q. But you'll also get more Q if the star is close to edge on, so high inclination. Because if you get to low inclination, then the polar spot will be in the center, and there isn't any polarization going one way or the other. So at low inclination, you're going to lose your Q. You're going to get the Q at high inclination. You're also going to get the Q at high beta. So the Q parameter likes high beta and high inclination. What does that mean? It means that you can think of diagonal lines as being the level of the Q. The more you go to the upper right, that's a high beta, high inclination, you're going to see high Q. So whatever Q you're measuring is like a contour that's diagonal in this plot. And notice how that's somewhat orthogonal to the way the interferometry works. Interferometry gives you a similar signal on a diagonal that goes from the bottom left to the upper right. Polarimetry goes the other way. So it's kind of like X marks the spot here when you combine interferometry with polarization, is you can narrow down, and depending on how precise your Q measurement can be, you can cut down the uncertainty in both the inclination and essentially, and most importantly, I feel, gravity darkening. The gravity darkening is about the physics of the interior of the star. What's making that star gravity darkening is the transport of light in its interior, and that's how we understand what's going on inside that star. So that's the fundamental game here, is to use all the information that we have available and not just throw it away. We're just throwing away the polarization because it's a little bit hard to detect. But if we use it, we can narrow the field and understand better what's happening in stars. Okay, now let's go back to the U for a second. I mentioned that in the U, there's a symmetry left and right. So if you just take continuum light, you're seeing everything you're seeing on this picture, and you're not going to get any contrast left and right. But you don't have to do this in the continuum. You can go to a line, like the interferometry did in H alpha that I showed you earlier. When you trace through the H alpha line, you trace across the disk, as the Doppler shift. You can do the same thing with a rotating star. As you scan over the line, if it's an absorption line, the line will work like a mask, shielding part of the star. It's like a negative signal instead of a positive one, but it works the same way. As you cross the line, you're blocking light from different places on the star. So that's a way of getting spatial resolution. Sweep the line, you're sweeping a mask across the face of the star. And so that's what gives you the line profile. But the line profile only has so much information. Now imagine swooping that across a signal like this, like the U signal. Now you see there is going to be a contrast. As you block off the minus polarization, you're going to see a positive signal. As you block off the positive, you're going to see a negative signal. So you will see a line profile in the U. If you're not doing it in the continuum where you get everything, you can pick where you are in the line. And you can also get information from the U. So you can get Q and U line profiles as you sweep across the star, adding significant amounts of spatial understanding of what's happening on the surface of the star. So, couples back to the
I guess this works.
So this goes back to, I showed you earlier the Q profile. This is the U profile, but the Q profile has this up and down characteristic as you sweep across. The U, if you think about it, would just go up once and then down as you cross first the minus and then the plus. So the shapes of the line profile are giving us information about the spatial resolution. And so you can model this. And so here's the Q over I and the U over I as we sweep through lines. So this is a spectrum of a bunch of different lines. And so this is modeling done by Daniel Cotton. And you see the Q profiles and the U profiles due to the structure on the surface of the star. So there's a tremendous amount of information in there. Now, a problem that you'll notice is if you check the vertical axis, this is parts per million, and it's like 20 or 50 parts per million. That is a very, very, very small signal. We do have polarizers with that kind of precision now, but barely. So this is just barely being able to see this. But this is in the optical. This is in the optical, and this is just about the worst possible place to look. Between 300 and 400 nanometers is the worst possible place to look for polarization, because you're going near an area where the polarization is zero. Polarization in the red and the polarization in the UV tend to be 90 degrees different. And somewhere in between, there's zero. So these models are done at the worst possible place to do polarization. But you do see you see what you would be looking to see, but just not at this level of signal. You go into the ultraviolet and ultimately the far ultraviolet, things get way, way better. So you can see what I was talking about a moment ago here. These are, again, plots that were done in the optical. The optical is easy to see. You can do it from the ground. So this is where the theorists start. But look what's happening. These are three different temperatures of stars, B1 through B5. The B1 goes through zero somewhere around 300 angstroms. B5 goes through zero somewhere around 4,000. So 300 nanometers, 3,000 angstroms, so 4,000 angstroms is the range where the B stars have their polarization go through zero. So that's not a good place to do polarization diagnostics. And you see in the red, it sort of flattens off. So it's not much better in the red. The place to do it is in the ultraviolet. We'll see in a minute. These curves go to very, very strong negative signals in the ultraviolet. Negative is just like which one, the vertical versus the horizontal. So the negative sign is arbitrary. The point is the size of the polarization is getting big negatively in the ultraviolet. But if you have to do it from the optical because you're doing it from the ground, then there's something to work with here. There is some signal here, 100 parts per million maybe, that's doable. Modern polarimeters are capable of this. It's just not a real issue. Let's go into the far ultraviolet and see what happens. This is the same thing we saw before. These curves are just different inclinations. So it likes big inclination. This looks like it's down, but it's down negatively. So this is like -3, -2. These are big polarizations. They're just negative because of the convention of the way Q is done. So this is actually a good thing that these are going down and getting to be fairly big, almost 1% in the negative direction. And you see where this is happening. Far ultraviolet, between 1,000 and 1,500 angstroms. This is Lyman alpha here. So that means you got to get out of the Earth's atmosphere. You have to have a satellite that is capable of getting the good polarization. So your options are this. You could do it in the optical and get weak polarizations, but you're doing it on an instrument that you're holding in your hands. So you can tinker with it and get it to be really, really good precision. Or you could say, let's go into space and get some serious polarization, but it's in space. So it's going to cost a lot more and you're not going to be able to tinker with it. So those are the choices you face. Ideally, you would do both because you want to understand, this is a prediction of a model that this will happen. So do we know that that's actually going to happen in real life? Not necessarily. So this is the closest connection we have to the internal physics of these stars. The physics we assume to make theoretical predictions like this is the thing that we can test, either doing ground-based polarization in the optical and looking for these really weak signals, or getting into space and looking for. And another thing I want to stress about these plots is you see two things here. You see an overall continuum level. So ignore the little bumps and ups and downs. You just see a continuum level. And that's what you would see if you have no no wavelength resolution. You just have a band, you're taking in all these photons, and a fraction of them, maybe 0.1% or so, are polarized. And so you can take that answer and compare it to the bottles, but it's just one number. Or you can go to higher wavelength resolution and see these line profile effects. That's what I was talking about before. Where in the line, you're not just taking in everything you see, you're sweeping across the surface of the star. And you're watching the polarization change as it interacts with the brightness of the surface of the star. So in the lines, you get a lot of additional information that isn't there in the continuum. But it's a narrower band, so you're not getting as many photons. So you're constantly having to make these kinds of trade-offs. Do I want to work from the ground where it's easy? Do I want to go to space where the signal is stronger? Do I want to look at the continuum where I can grab huge chunks of light and get lots of photons? Or do I want to go into the lines and winnow down my photon count dramatically from that? So there's a lot of interesting trade-offs you have to decide as an observer on how you want to attack this problem. Okay, so the bottom line is polarization gives us these independent constraints. It's not like the polarization by itself is going to answer all questions. It's like we have a bunch of questions and we only have so many constraints on it. It's not enough. We have ambiguity. We need to use all the information that's coming to us. So that's going to require getting the polarization piece. And at times, the polarization piece is, in some sense, orthogonal to the information that we were getting already. The polarization can also address a lot of different ways that the symmetry is broken from spherical. So far, I've only talked about rapid rotation of the star, but there's many other connected things that happen to stars. Now, this acrinar here is a star that spun out a disk. The way DP stars work is sometimes they have disks, sometimes they don't. Acrinar showed us a disk coming that was actually captured in interferometry. But Acrinar is a very close BE star. So, we can use interferometry and wait for the nearest ones to do this, or we could try to extend our reach with polarization. This does not require a large angular size of the object. Also, you can see the disk itself in polarization. This is a degree disk around Beta Pit, so this is dusk. So this is the place where you see a lot of the polarization measurements being done, is in dusty disks, because the dust will polarize light in a way that's very similar to how free electrons do it. And so polarization measurements of the disk, again, it's because the light comes from here, it bounces you in this direction, it's going to be polarized this way. If it bounces you in this direction, it's going to be polarized this way. So polarization is already being used in degree disks. We're talking about a similar kind of thing in electron scattering disks. Binary reflection produces polarization. Talked about the importance of binarity in producing rapid rotation in stars. If light from one star bounces off the other, it's going to be very polarized. So, and this will go around. So you could watch this in real time, and depending on the attributes of the orbit, you'll see time-dependent changes in what's happening with polarization. So you can learn about binarity with polarization. Here was a model done on a Wolf-Rayet wind that has a companion where the O star is orbiting the Wolf-Rayet wind. The Wolf-Rayet wind is almost like a big star itself because it's optically thick ring. Maybe that big star is not spherical because the ring is not spherical. Now you have a polarizing source of light to bounce off that Wolf-Rayet wind going around. What's that going to do to the polarization as it goes around? Useful constraints on that as well. And here's maybe the last special case I'll talk about, the Beta Lyrae, which was seen by Whoopi. So Whoopi was our first example of using the UV to look at polarization. It was done from the space station, so very jerky and so forth. But it did have some important discoveries. For example, it discovered this position angle, 90-degree rotational position angle. That's another thing that polarization tells you. It tells you, is it polarized vertically or horizontally? A 90-degree position angle switch means that in the optical, we see it polarized one way, vertically. That's what we're seeing in the optical. So we were seeing light bouncing off the disk in the optical, and it was polarized vertically. Then in the ultraviolet, it switched by 90 degrees. We were seeing light that was polarized horizontally in ultraviolet. And so the model that was risen to the fore is that that's because there's accretion. This is not a decretion disk like a PE star. This is an accretion disk, the making of a rapidly rotating star. The mass is coming in, making an accretion disk, and some of it is leaving. It's a non-completely conservative transfer process. And so you see the disk in the optical from this position angle. There's the optical, that's a vertical position angle, and here's the horizontal position angle. So that's the kind of information you can get from polarization, especially if you connect the optical regime to the ultraviolet regime. So there's a lot of power in the ultraviolet regime. Other things, here's the homunculus nebula, it's polarized. I mean, anything that is highly non-spherically symmetric is going to give you some polarization. So I know we're short for time, so I'm going to go right to the conclusions and leave some time for questions. So the conclusions are, okay, polarization is the missing piece when it comes to diagnostic constraints on stars. We're not really taking advantage of it, especially in ultraviolet, because it's very weak. It's a very weak signal. But that's the whole point of it, because it would be zero in complete spherical singularity. So anything you see is an example of geometry constraint. And in lines, you can sweep the face of the star to give you more information, but fewer photons. The main thing is it couples to the brightness contrasts, because we have that plus and minus. It's like being able to pass a plus and minus mask over the face of the star to bring out the contrast in the star, learning about things like gravity. It's very complementary to the diagnostics we now have, and this goal is to solve ambiguities and open a new window to understand. And so that's my final pitch then, is I'm involved with this satellite proposal called Polestar. And so what we want to do is we want to have an ultraviolet spectrometer in space. We have one now, it's called the Hubble Space Telescope, but we're not going to have it forever. So let's keep an ultraviolet spectrometer up there. And at the same time, when we're doing that, let's throw a polarizing capability onto it. We can detect polarization and take advantage of all this stuff, especially given the importance of rapidly rotating massive stars. So that's the picture. Okay, I'll close there. Take questions.